All right, so I'll just finish off the lecture that I started on Monday and we didn't get to finish. Um, Today's probably going to be a short lecture. We'll just end it a little bit early. We'll let you guys go go a little early for Friday, and that will be it. Um, so so anyway, we left off. We were talking about SVM. Okay, so an SVM, the idea, we started off with just kind of this concept of this maximum marginal linear classifier. And so you just want to kind of create this this boundary where the distance is as wide as possible. And basically, you've got these parallel lines, and we do it in such a way that, the distance between this parallel line and this parallel line, that this is going to form the boundary. And the line in the middle forms the boundary region. These two parallel lines we want as far apart as possible. And basically, when we do that, we're going to basically take 2 points that lie on that boundary, or lie on kind of these dotted lines here, these parallel hyperplanes, and we project that onto some vector that lies perpendicular to the boundary. Okay, and we talked about this, and we said, what we want to do is we want to maximize this, but according to these conditions that when we draw the boundary, that everything has to be classified correctly. Okay, so we're going to try to take this thing, we project it onto some vector w, and then the vector w is this whatever direction this is, and we say, well, what vector w should we pick? And basically we just want to maximize this thing. Okay, so we want to maximize this, but there's a bunch of constraints in that we can't just pick some arbitrary w. It has to be one where that when we do go through it, all of the points are classified correctly. And so we use this, we have this Lagrange multiplication, we use a bunch of Lagrange multipliers, and we have to kind of figure out what these values should be. And effectively, the values that do count towards the calculation of the boundary are used, and then the other ones are not. Okay, and those form the support vectors. And we kind of left off, and we said, we have this thing where we can allow for soft margins. Okay, and soft margins basically allow for some points to be misclassified, right? And that feels a little bit silly because we were just saying, like, when we draw the boundary, all of the points have to be correctly classified. But now we're going to kind of add some kind of weights to these things and say, you know what, when they get misclassified, depending on how far off they get misclassified, we'll have some kind of penalty factor there. And so, now we're kind of maximizing, we still want to maximize this distance, but the distance is now, it's a little bit more calculated in this slightly different fashion, where we allow for some misclassifications, we allow for things to fall within the boundaries. But so far, we've been just looking at this linear linear boundary, okay? And today we are going to look at nonlinear boundaries, okay? And so the function that, again, we're trying to maximize is, we're trying to maximize this same function, which again is the result of trying to maximize this quantity w, okay? That maximizes the margin, okay? And we've just kind of created this alternate formulation for that using the sum of all of these Lagrange multiplier constants, okay? And when we do that, there's this cross product, this x transpose x, okay? One, and we're looking at kind of the cross product between basically every combination of points. You have big N points, and we're looking at, point M time multiplied by point N. We're looking at, the relationship between all of these different points, and we optimize this in such a way, and we have to look at this. Okay, now what we can do is we can replace this cross product with something called a kernel function, okay? And basically the kernel function is another form of a cross product, but we apply some kind of transformation to it, okay? And this sounds all very confusing, but maybe with a little example, it will make a little bit more sense, right? So if you do X transpose X, basically you're just kind of doing this dot product, right? You're just taking X transpose X, you're taking, the first element of XM and the first element of XN, you multiply those together, you take the second element of XM, the second element of XN, you multiply those together, the third element of XM and the third element of XN, and you multiply those together and you add them up, okay? And basically, when you do a kernel function, you're doing something similar, except when you take X, you apply some kind of transformation, XM, you apply some kind of transformation to it. You take XN, you apply some kind of transformation to it, and then you do a cross product there, okay? Or dot product there, okay? And so this is basically what we're saying here, is that the kernel function between some vector XM and another vector XN is going to be the inner product or the dot product of vectors after we apply some kind of transformation function phi. And I don't know what happened in my notes. I have this version of phi and this version of phi. It should be the same version of phi, but LaTeX is giving me different versions of phi here. But you apply some kind of transformation function phi that's going to take your vector xm and turn it into another vector. You take another vector xn and you turn it into another vector. And then you're going to take the inner product or the dot product between those two transformed vectors. Okay, so here's one example. This is just an example. There are lots of different possible transformation functions. Okay, so one example function here is we're going to take a two-dimensional point. So x exists in two dimensions. It's an x1 and an x2. And we're going to transform it into 3 dimensions. Okay, and the transformation is very simple. We will keep x, we'll preserve x1, we'll preserve x2, but the third dimension is going to be x1 squared plus x2 squared. Okay, and so let's say we have two vectors. Okay, xn is 1, 1, and xm is the vector 5, 1. And what we're going to do is we are going to take, we're going to transform this, okay, using this, all right? So 1, 1 becomes 1, 1, 2, right? So we preserve x1, 1. We preserve x2, which is also 1. And then, but the kind of the third element in this vector is going to be x1 squared plus x2 squared, which is going to be 1 plus 1 squared plus 1 squared, which is 2, okay? And here I have 5, 1. 5, 1 will become the vector 5, 1, and then we do 5 squared plus 1 squared, and that becomes 26. Okay, so we take the two-dimensional vectors, we apply some kind of transformation phi to it, and then we have, now I have a three-dimensional vector, and I'm going to take the inner product or the dot product of this three-dimensional vector, these two three-dimensional vectors, and so I do 1 times 5 plus 1 times 1 plus 2 times 26. Okay, so 1 times 5 is 5. 1 times 1 is 1, 2 times 26 is 52. I have 5 plus 1 plus 52, and that gives me 58. Okay, and so this kernel function, when I take the inner product of these transformed vectors, is 58. Okay, but kind of the key here is that depending on what this transformation function is, you can calculate this number 58 directly from xm and xn without needing to actually do this transformation. You don't actually, so the idea is you're transforming it and then you take the inner product and you get some number. But a lot of times there might be some corresponding function that gives you this number 58 directly without needing to do the intermediate step of transforming it from 2D into 3D, okay? And so if this is the transformation function phi, the corresponding direct kernel function is this, xm transpose xn plus norm xm squared plus norm xn squared. So if you do this, this will give you the same result as doing this, as first transforming the function into 3D and then taking the inner product. You can get that same number, that 58 or whatever it is, by just computing it this way. Okay, so it's not actually necessary to use this transformation function phi to actually kind of project from 2D into 3D. You can actually use the kind of kernel function directly to get the resulting inner product here. Okay, and so so let me just kind of demonstrate this here. All right, so here we have xm transpose xn plus norm xm squared plus norm xn squared. Okay, and so if I do that, my vectors, the original vectors are 1, 1 and 5, 1. Okay, if I take the inner product of 1, 1, 5, 1, okay, that's going to give me 1 times 5 plus 1 times 1. Okay, so this will give me basically 6 over here, right? The inner product of 1, 1, 5, 1, I'll get 5 plus 1 is 6. And then over here, I do norm 1 squared. So basically 1 squared plus 1 squared times norm 2 squared, which is 5 squared plus 1 squared. So I do the product here. I get 2 times, this is 26. And so this becomes 52. And here I also get 58. Okay. And so I can get the same answer, and we can see that we end up doing the same kind of products here. We get 58 here. The other option is I could apply the transformation function, which gives me 1, 1, 2 and 5, 1, 26. And then I can do that, put it into 3D and then get the inner product this way. Right. So all to say is that we don't actually have to figure out what the 3D vector is. We can just take the original 2D vectors, but get the inner product of what the transformed vector is without actually doing the transformation itself. Does that kind of make sense? So what we want to do is we want, I'm trying to think of some kind of analog, is basically we just want the answer. We don't actually care what happens in between the beginning and the end. We just want the end product. Okay. And so the proper way is, you send it off to get transformed into 3D. You do the inner product at the 3D and you get this result. Okay. But you can actually get the same result just by kind of using this kernel function. There's often some equivalent kernel function. Now, I guess not every transformation function has an equivalent kernel function, but the ones we're going to look at do. Okay. And not every kernel function has a transformation function that we can express easily. All right. So why do we want to do this? Okay. Well, the reason why is sometimes you'll have a set of points that when they're plotted in 2D space or whatever current dimension they exist in, they are not linearly separable, right? So far we've been talking about the maximum margin linear classifier, and you need to draw a straight line in order to separate the two classes. But a lot of times you have these cases where they can't be separated linearly. And so what you can do is you can take your data and you can project it into a higher dimension, like take your 2D data, project it into 3D. And then once they're in 3D, you can actually draw a linear hyperplane. Basically, if you're in 3D, you draw a plane. You can project it into an even higher dimension, and you'll have some kind of linear flat hyperplane that we can use. Okay, so here is a video. Let me this is a video that we'll look at here, and let's click play here. Okay, we'll watch this a couple times. All right. So this video was created in 2007, and so this is back when like the highest quality is 240p or something. I don't know. This, unfortunately, it's very blurry, but I don't know if you can see there's blue dots here in a circle and red dots all around outside, okay? And we cannot separate them with just one straight line boundary, okay? We need, some kind of round boundary here. So what we're gonna do, what we do is we use a polynomial kernel, much like the one I've used, where we're going to take this two-dimensional data and project it into 3D, okay? So here's the 2D data, and this is basically, we're gonna preserve where x1 and x2 is, but the dots themselves are gonna get projected basically to x1 squared plus x2 squared. So basically, the distance it is from the center, the origin, is gonna kind of determine how high they get projected. So dots near the center of this graph, let's say this is the origin, okay? The origin will be here, they will be low, and then dots that are far from the origin will be high, right? So we're looking at x1 squared plus x2 squared. So here's 0, 0 is gonna be low, x1 squared plus x2 squared, let's say this is 10, 10, is gonna be at, have a height of 100. Over here is negative 10, 10. Well, I guess 10 squared plus 10 squared will have a height of 200. This will have a height of 200, et cetera, et cetera. Okay, so that's what we're going to see. We're going to see it start off here. We're going to project it basically to like x1 squared plus x2 squared. Okay, so it gets projected like this. Okay, so this now the data exists in kind of this three-dimensional space, right? So we've added a basically a third coordinate. Okay, so the data started off in 2D, but we use that transformation function phi, and now the data exists in 3D. And now that the data is in 3D, we can draw a linear plane, okay? This linear plane separates all of the blue dots from the red dots, okay? So in 3D space, the equivalent of a linear boundary is a plane, and now we have a linear boundary in three-dimensional space that separates the blue dots from the red dots. Okay, and so now that we've created this boundary here, we can see what, quote, shadow it casts in its original 2D space. And that boundary looks like a circle here. Okay, so again, the data starts off in 2D. We have some kind of kernel here, and I'm pretty sure the kernel that they're using is basically x1 squared plus x2 squared for the third coordinate. We're preserving the x1 and x2 locations. And then once we're in 3D, we can draw a linear boundary, in this case, a plane, and that plane separates the blue and the red. Okay, and this is great, right? I love short videos that explain exactly what we need to see. There's no 10-minute story about and nonsense. Okay, so that's great. Does that kind of make sense what's happening? Okay, so we're basically taking that, the data started off in x1, x2, and then we projected into a 3D by having the 3D coordinate as x1, x2, and then the third coordinate is x1 squared plus x2 squared, and then we separate this, right? Okay, and so we have a question: is projecting to just 3 dimensions typically enough to ensure linear separability? Generally, no. Generally, no. Okay, I'm starting off with 3D, this going from 2D to 3D example because it's easy to visualize. But oftentimes we will project it from 2D into a much higher dimensional space, like, I don't know, 17 dimensions, possibly even infinitely high dimensional space. And which is actually what happens with the radial basis kernel or the Gaussian kernel. It actually projects it into this infinite dimensional space, which we can't even picture or imagine. But somehow there is some kind of linear boundary that exists in this very high dimensional space. Okay. And so there are all sorts of kernels that we can use. You can click this link for the positive definite kernel. Okay. And so geez. Okay, yeah, here they are. So that we have the linear kernel, okay? And then you have polynomial kernels, which is you take x, y, maybe add some kind of constant and raise that to the nth power, okay? You have the Gaussian kernel, which takes basically the difference between x, y, and we do e to the negative of that thing squared, okay? And then, you know, there's some constant in here and stuff like that, okay? There's all sorts of stuff. I would say the Gaussian kernel is a commonly chosen kernel because it offers quite a bit of flexibility, but the polynomial kernel can also be used, okay? So the commonly used ones are the Gaussian and the polynomial kernel. And so the Gaussian kernel is actually, it's based on the Taylor expansion of the exponential function. And so the Taylor expansion of the exponential function is technically this infinitely, not technically, it is an infinitely long series. And so what it's doing is it's taking basically every element of that infinitely long series and it's projecting our data into this infinitely high dimensional space. Now you can get something that's approximately that by truncating it, okay? But then then the equivalent kernel function is not exactly e to the negative this, it's going to be approximately this, okay? So anyway, that's what we do. And so there's actually no point, you know, if you're dealing with something like the Gaussian kernel, there's no point in actually trying to figure out what the transformed vector looks like. Okay, so when in our example, we went from 2D, we saw the vector in 3D, and then, you know, we can plot that and we can calculate the inner product. When you use something like the Gaussian kernel, you just have to kind of say, all right, it's going from 2D into infinite D, and there's no point in trying to figure out what that infinitely long vector is and what that would look like plotted. You just have to say, all right, this is somehow going to work, but we can get the inner product. Okay, we can, it's, even though it's infinitely long, the inner product is a finite number, right? So we, you know, just like, even though the normal PDF goes from negative infinity to positive infinity, the area under the curve is a finite value 1. And so, you know, kind of similarly, even though these vectors, these is infinitely long, the inner product is a finite number, and we don't actually have to transform them. We can just use the kernel function directly, and it just kind of plugs into this solution, not solution, this equation that we're able to maximize using quadratic programming, which I still don't know what it is or how to do that, but we can still kind of plug it in here and arrive at some kind of solution for what that boundary should be. Okay, and so so the example here is we've got, you know, this this is the same data that I put into your homework, and I asked you guys some questions about this. You know, here's this data. It is clearly, we cannot draw some kind of linear boundary to separate this. But what we can do is we can start projecting this into higher dimensional space. You know, I've totally forgot about giving you guys your view quiz answers. I've given you 0 so far, or have I given you 1? 0. Okay. Let's go ahead and give you your first 2 view quiz answers. The letters B and C. B and C. B as in bear, C as in cat. B and C for your first two answers. Okay, so we can't separate these linearly. Okay. If I tried, this is what it'll kind of look like. All right. And, you know, this is clearly, you know, we have to use some kind of soft margin to allow for misclassifications. And then we just say, okay, well, this side is going to be red and this side is going to be blue. And here I've arbitrarily chosen these boundaries of 0.5. Technically, these parallel lines, maybe I probably should have done 1 and -1, which would have aligned a little bit more closely with kind of the diagrams I were drawing back here. This is where this would have been labeled +1 and this would have been labeled -1. But I think I was just following some example that somebody else had where they used the boundary parallel lines of 0.5 and -0.5. And so that's what we have here. But this is what a linear kernel would look like. It doesn't do a great job, okay? So what we can do is we can use a polynomial kernel. And, just like in the way that a polynomial function, when you have higher degrees, will give you a more flexible function with as you increase the degree of your polynomial here, you'll get a more flexible boundary. So what this will do is it will project our data into some higher dimensional space, not exactly three-dimensional space. It ends up being something a little bit higher dimensional than that. And this is what the boundary that gets drawn looks like, okay? And these lines are technically parallel planes, okay? So in the higher dimensional space, you can imagine planes that are parallel to that boundary plane. And those parallel planes, when they get cast back down into 2 dimensions, would kind of draw these lines. And so these lines that they are not parallel in 2D, but they are parallel in this higher dimensional space that it exists. Okay, so this is the shadow of the boundary that gets cast when it gets cast back down into 2D. So in higher dimensional space, you have these parallel planes, and then we're just looking at the shadow of the boundary down in 2D. Okay, so that's degree 3. If I increase the degree to degree 5, it looks like this. This seems weird. Okay, I don't know what this is, but apparently, I'd say, so well, what kind, how do I know what degree polynomial should I use? We don't know, okay? We don't know. There's no easy answer. The answer is always, it depends. Use cross-validation to check your performance, okay? This is, everything in SVM is a bit of a mystery. I mean, not completely. Like, we have an idea of like what these things do. We know if you increase your degree, you're going to get a more flexible boundary. There's another parameter called the cost that also kind of pushes the boundaries around. But the answer is you're going to have to use cross-validation to kind of test out your performance. There's no quick and easy answer as far as what numbers you should use, okay? So this is just polynomial degree 5. I could keep increasing the polynomial degree. I would say more common choice is the Gaussian kernel, all right? And here we're gonna, when you deal with the Gaussian kernel, there's two parameters to mess with, the gamma and the cost, okay? The gamma is kind of like how, like if you draw the boundary, how flexible is this boundary going to be? And so a very high gamma allows for this very wiggly, squiggly boundary. A low gamma will try to be something that looks a little bit more linear, okay? Cost is kind of how much penalty gets applied every time there's a misclassification, okay? If the cost is very high, it's going to really try to avoid misclassifications. And if the cost is low, it's going to say misclassification is not so big of a deal. Okay, so here I've got a fairly low gamma and a fairly, I guess, a average size cost or something. And this is going to be kind of the boundary that gets drawn. Okay, and again, the thinner lines are parallel planes. Okay, in this high dimensional, in our case, infinite dimensional space. All right, here I'm altering gamma, okay? If I decrease my gamma to 0.1, we can see the boundary gets a little bit, it tries to be a little bit smoother or more straight. Here, I'm going to keep cost at 1. I'm going to slowly increase the gamma from 0.1 to 0.3. We get a little bit more flexibility, 0.5, more flexibility, 1, more flexibility. Is 1 the default gamma? I think it is. At gamma 2, it's more flexible. Gamma 5, it's even more flexible, and things like that. Okay, here's gamma 10, and now we get this really squiggly boundary. Okay, and this is my analogy here. Here I've got this HDMI cable, and I say, like, what if you have like these dots on a surface here? Okay, and I say, all right, I want you to kind of bend your HDMI cable to kind of form a boundary, right? This is kind of a thicker cable. It's a little bit harder to form like these really sharp twists and turns. Okay, so this would be kind of like using a lower gamma, right? Here is like an iPhone cable. Okay, it's a lot more flexible, right? And so you can get kind of like tighter turns. This would be equivalent to using a higher gamma. Okay, and if you had a piece of string, and I had a piece of string or a thin piece of string, I don't know where it is. Okay, well, here's a little thing, you know, like this is like a little piece of string from a gift bag. You know, you could make this wind up the corners as tight as you need to do, right? And so that would be using like a very high gamma, and a lower gamma would be having kind of like this fat cable that's harder to manipulate, right? So this would be like what you can do if you had like a fat hose that's like hard to bend, and this is like as much curvature as you can get, right? And this is like using thinner and thinner cables where you can kind of like bend them around and stuff. And at a high gamma, you got this, okay? Here, if I keep gamma, here I'm gonna maintain gamma here, and what I'm gonna do is I'm gonna mess around with the cost, okay? And so let's just see what happens. Gamma is 0.5. If I mess around with the cost, what happens, okay? So gamma being stuck here, it's kind of like using a certain kind of cable thickness, so you don't have a whole lot more flexibility. But what we're seeing is that it is getting bent into kind of like, here it was kind of a lot smoother. And as I increase the cost, we are getting sharper corners. So what's going on, okay? What's going on here is that as we increase the cost, okay, keeping the gamma here, we're sticking with this kind of this cable with a certain amount of flexibility. Increasing the cost is kind of like allowing each point to exert more force as far as bending it, right? So if I'm like exert a lot of force into bending this, I can get a tighter corner, okay? Kind of like what's happening here, okay? But we're saying each point is exerting kind of like more pressure and more influence, right? As far as what it's doing, okay? And similarly here, we're gonna keep gamma at a higher level. So now we've got a more flexible thing. And then with the low cost, each point doesn't exert that much force on the line, okay? But as I increase the cost of the points, okay, we can really force, you know, tight twists and turns in the boundary that gets drawn, okay? And so I've drawn a bunch of these things, okay? I pretty much have the same thing in your homework, okay? So in your homework here, I've got a high gamma and I'm messing around with the cost, okay? So same thing in the homework. I think in your homework, just because I didn't want your homework to, I mean, not that it matters, you're not printing it out, but there's only like a small subset of these pictures in your homework, okay? But you can look at the same slides where basically the same kind of concept here, where you can say, well, what happens when you mess with the gamma? What happens when you mess with the cost? And I want you to kind of just think about it and write about it in the homework. So I think that's it. I don't know. Did you guys have any questions about SVM? Just kind of this high level overview of the subject. And again, you know, what gamma should you use? What cost should you use? The answer really depends on whether you want a model that's very flexible or not, and usually you use cross-validation to kind of estimate. What are the benefits of SVM over other classification methods? Oh, geez, these are hard questions. When were they made? What is the history of SVM? I don't know. No. Support vector machine, School of Veterinary Medicine. We want the support vector machine developed by Vladimir Vapnik in the 90s, okay? Supervised learning for classification are one of the most robust prediction methods, being based on statistical learning or VC theory, Vapnik-Chervenikis theory. I don't know what that is. Proposed by Vapnik. Who is this person? Russian, 1936. One of the main developers of this and the co-inventor of the support vector machine. Wow. Wow, look at you. Okay. Very good. Yeah. I don't know. I guess people, you can try using different kind of machine learning techniques for things, and in certain cases, support vector machines have actually worked well. Yeah, he's a lot of these people who've developed things are still alive. So because a lot of these things are fairly recent innovations. We're not talking about like discovery of like oxygen or something, you know, like this has been around more recently, right? And a lot of these things, like only recently have the computational powers been strong enough to do this. You can do regression with support vector machines, but how does that work? Oh, I don't know, actually. Support vector, linear SVM, this is the hard margin, the soft margin, and nonlinear classification. And we have all of these Gaussian kernel things, computing this, the kernel trick. Oh, look, there's almost the same example that we have. Look at this Wikipedia page. I almost think I copied this, but I promise I didn't. I just was based off of the textbook. Okay. I don't know. So, you know, I've seen image classification use support vector machines. It was on, they did it for like facial recognition things that were using support vector machines, but I don't remember. I don't remember any of the details, but I remember seeing that as like as a use. And I think a lot of these things, when you have some kind of problem where you're not quite sure, you kind of just try a whole bunch of approaches, right? And in some cases, like linear regression will get you really far. Logistic regression can get you really far, and you can be like, hey, this is pretty good. I understand what's happening, and in those cases, like just stick with that, right? But in some cases, you're like, oh, well, you know what? Let's try this kind of classifier. Let's try a support vector machine, and maybe you can squeeze out, you know, 0.5% performance increase. And you have to say, well, you know, is it worth it? And sometimes it is, and sometimes you're just like, you know, it's not worth the extra hassle, and the now everything's a mystery. So a lot of these kind of quote classical methods, you know, they still hold their own. So linear regression, logistic regression, still very powerful tools that I recommend. Try the simple approach first, and then once you get something working there, then you can try something else. You can try the support vector machine. You can try the neural network. Those are popular these days, and you can see how well they perform. Using the decision function instead of taking the sign of it. Yeah. So, okay, we'll call it here. Did I give you your last view quiz answer? No. Last one for today is D. D as in dog. D as in dog for the last view quiz answer. All right. We'll end here. Have a good weekend, you guys, and we'll see you guys on Monday.